one of the most generally perceivable physicists, Michio Kaku, has discussed his evaluation concerning this issue. Kaku, known for his astonishing commitments to the fields of genuine science, has actually perceived that the James Webb Space Telescope has seen 6 huge vast designs that experts once thought illustrated unequipped for existing. These openings can possibly open up new points of view on how we might interpret the universe. It is, in this way, both hypnotizing and worth paying special attention to these developments. Kaku is an important figure in the logical field, a physicist of American and Japanese legacy. He is seen as an expert in both ordinary exploratory physical science and quantum mechanics. Dissimilar to some more moderate and doubtful experts, Kaku doesn't have a place with that bunch and has been open to the stunning later discoveries of the James Webb Space Telescope, JWST mission. We are lucky that this perceived master has chosen to end his silence and deal clearly with what can no longer be denied. The excitement and, essentially, thorough tone of the notable physicist are clear in his comments on the discoveries made by the James Webb Space Telescope. He recommends that these revelations have been the part that has strengthened his interest. We should analyze the repercussions of Michio Kaku's disclosure of these 6 huge enormous systems. Kaku is a researcher who has consistently had the capacity to think about new speculation throughout his life. He values that Einstein's hypotheses of relativity and Newton's regulations are deficient to grasp the full diverse plan of the universe. Kaku comprehends that the openings of the new telescope could fundamentally work on the logical field, despite the way that numerous of his companions have not had the option to embrace this view. This has caused concern and anxiety among both allies and pundits of quantum mechanics. Anyway, this affirmed understanding brings out giggling from Kaku. The JWST has uncovered the revelation of 6 gigantic universes tracing all the way back to the earliest times of the universe. Every one of these enormous systems contains a greater number of stars than our own, notwithstanding framing just a short time frame after the Big Bang. The gathering of cosmologists who made the disclosure has named these amazing frameworks universe breakers, as their world would change our whole comprehension of the universe. Something here no longer fits with the hypothesis of the Big Bang. The theory of the universe's origin lets us know that the universe was a tempestuous spot following the start event. The first solid objects took a few 100 million years to form, and it required perpetual extra years for these items to accomplish a sufficient thickness to produce light. The improvement of complicated plans like systems should happen a lot later. A portion of the newfound frameworks surpass the size of the Milky Way. Also, their monstrous heavenliness suggests that they were conceivably forming some new stars every year, while our own galaxy forms stars just inconsistently. It remains disputed exactly when the first universe formed. Researchers have not had the option to decide this until as of late. The one thing that is clear is that, initially, there might have been simply single stars or gatherings of stars that eventually came together to form increasingly larger structures, eventually leading to the development of dwarf galaxies, which went through consolidations and continuously evolved as shown by past hypotheses. As indicated by these speculations, very advanced and gigantic systems proved unable to have existed around that time, which brings up the issue of whether the universe is really more seasoned than recently recognized, or whether complex, large-scale structures existed much sooner than guessed. This current circumstance is trying for conventional science, which still battles with this model. Moreover, a few areas of physics have firmly excused this revelation, highlighting expected blunders in the age estimations. Kaku, mindful of this, had this to say: "There are many occurrences of old and deluding speculations that tenaciously continue due to the conspicuousness of certain specialists. Many of these theories were eventually disproven when central assessment uncovered their distortions. Subsequently, the fundamental work in any science, especially in physics, rests with the experimentalists who maintain the validity of assessment through exact truth. On Earth, we have basically no information on the genuine beginning characteristics of the universe. The Big Bang theory was spread out in 1927 based on observations of the universe's expansion. This data led to the conclusion that the universe began from a singular point and has been growing from that point forward. At the time, it was hard for people and researchers to envision a universe with a start and an end. The plausibility of a universe that had continuously existed and was boundless in time was beyond human imagination. In fact, even today, researchers still face difficulties in figuring it out. Anyway, it is critical to reconsider these potential outcomes. These new insights don't fit with what researchers have relied upon for a long time in the theory of how things came to be. By and large, science has repeatedly shown that reassessment and openness to big ideas are important parts of the scientific process, just as much as the affirmation of explicit theories and observations. When Einstein was a young researcher, he believed planets were fixed in the universe and these particular plans involved a defined space. Anyway, we now understand that everything in the universe is moving. Planets orbit stars, stars move within their galaxies at different rates, and whole galaxies move quickly through space, the ultimate destiny of which we still can't predict. Today, examiners are challenged to accept uncomfortable discoveries, and it is understood that theories are not simply hypotheses or large insights until they are fully tested or confirmed by indisputable observations. The probability of the Big Bang arose from the affirmation that galaxies are moving away from one another and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding for a long time. Extra evidence, like cosmic microwave background radiation and the redshift of light from distant galaxies, as well as other cosmic patterns, seems to support this theory. Anyway, it is essential to recall that those who once believed the Earth was flat, and that the sun revolved around us also had similar types of evidence for their doubts until events or technological advancements gave a clearer picture. As of now, we are seeing a similar situation. Researchers anticipated the JWST to validate instincts about the Big Bang. Anyway, rather, they have found 6 systems that appear too large for their age. This reminds us that science is continuously evolving, and specialists must remain open to new discoveries and reassess existing theories based on available evidence. Researchers use redshift as a tool to determine specific measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to one another. To understand this, imagine watching a car coming toward you. As it draws closer, you hear the motor getting louder, but once the car passes you or moves away, the sound changes. This is because the sound changes as the vehicle moves. The same is true for light. When a light source, like a distant star, moves toward us, the light we see shifts toward the blue end of the spectrum. Alternatively, when the light source moves away, the light shifts toward the red end. This phenomenon is known as redshift. Physicists have converted redshift values into speeds and distances for surveying amounts in the study of the universe. However, it is important to note that small errors in these computations could have significant implications. The estimation techniques used in the past are now under review, and the results that researchers will arrive at concerning the latest discoveries related to our universe are exciting. It is essential to consider whether these results are truly based on redshift mistakes or whether some researchers are simply denying the facts. This is a question that requires serious evaluation and a careful review of the data and techniques used in the study. As scientific inquiry advances, discoveries made by instruments like the James Webb Space Telescope often challenge our assumptions about the universe. The ongoing discovery of 6 massive galaxies tracing all the way back to the start of the universe is one such example. These systems, which defy the standard theory of galaxy formation, raise fundamental questions about the timelines and processes involved in the development of large-scale structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with state-of-the-art technologies that allow it to peer further into space with striking clarity. Its ability to detect light from the farthest reaches of the universe gives cosmologists a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models that predicted such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond cosmology and into the realm of fundamental physics, compelling researchers to rethink established theories about the early universe. These discoveries also highlight the importance of remaining open to revolutionary ideas and updating our understanding based on empirical evidence. Kaku has emphasized the pivotal role of scientific validation in shaping our perspective of the universe, pointing out that theories must continually evolve to accommodate new data. The debate sparked by these revelations reflects the dynamic nature of scientific inquiry. On one hand, There are supporters who argue that the discovery of early massive galaxies suggests a longer timeline for galaxy formation than previously thought. This viewpoint challenges the traditional view that galaxies evolve slowly over billions of years through mergers and the gradual development of smaller objects. On the other hand, cynics caution against quickly discarding established models based on limited observational data. They advocate for a more cautious approach, suggesting that discrepancies in data interpretation or measurement errors could explain the startling findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a critical role in these fundamental assessments. As galaxies move away from Earth, the light they emit shifts toward longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy's light spectrum, cosmologists can deduce its distance from Earth and its speed relative to us. This data provides key insights into the expansion of the universe and the dynamics of galaxies. The combination of redshift data and advanced telescopic observations has led to remarkable breakthroughs in understanding the universe. However, new findings like the 6 massive galaxies discovered by the James Webb Space Telescope present challenges to the current understanding of cosmic evolution. As the scientific community continues to evaluate and refine models of galaxy formation, these discoveries highlight the ongoing dialogue between theory and observation, where new data has the potential to reshape our understanding of the cosmos.